Hi everyone, welcome to our 48th seminar of the Centre of Research Excellence in Aphasia Recovery and Rehabilitation. I'm Dr. John Pearce, postdoctoral researcher at the Aphasia CRE and facilitator of this seminar series. Before anything else, I'd like to just acknowledge the traditional custodians of the lands where we and many of our participants are located on across Australia. I'm on the territory of the Bunurong people of the Kulin Nation, and we pay our respects to elders past, present and emerging, and extend this respect to all Aboriginal or Torres Strait Islander people viewing this seminar. This morning we're hearing from Alexandra Salem, who's joining us from Oregon in the United States. And before I introduce Alex more formally, allow me to just explain how you can ask questions about the topic being presented today. So during the presentation, if you have any questions for Alex, please submit them using the Q&A feature located in the Zoom toolbar at the bottom of your screen, rather than the chat function. And you can enter those questions at any point throughout the talk. In fact, entering them before the presentation finishes is probably better because it allows the audience to indicate which questions are of most interest to them. So you're able to like any question that you find particularly interesting or relevant, and I'll be asking those questions in order of popularity. Just a reminder to please submit brief questions and no comments, please. Alex will address as many questions as time permits at the conclusion of the seminar, and the co-lead investigator of this project, Dr. Gerasimos Fergadiotis, is also joining us to answer any questions. All right, now I'd like to introduce and welcome today's distinguished speaker, Alexandra Salem. Alexandra works as research staff for the Department of Medical Informatics at the Oregon Health and Science University. She has an undergraduate degree in mathematics from Reed College and a Master of Science degree in computer science and engineering from the Oregon Health and Science University. Her work focuses on automating assessment of speech and language disorders using machine learning and natural language processing. She's particularly interested in applications of computer science to aphasia research. So Alex, thanks for agreeing to present today. It's always nice to have someone from who's not a speech pathologist working in aphasia. It's always a great new perspective to have.
Yeah, thank you so much for having me. I'll go ahead and share my screen. Let's see. Okay, how does that look?
That's great.
All good?
Yep.
Okay. So, yeah, thank you again for the introduction. So, my name is Alexandra Salem. The title of this talk is Automatically Assessing Paraphasias in Discourse, Breakthroughs, and Remaining Challenges. So first I wanted to kind of introduce our team. So all of this work has been really highly collaborative. And so I really wanted to emphasize, I'm presenting this, but we've all contributed a ton to all of this work. And I also wanted to emphasize the interdisciplinary nature of our team. So we have two co-PIs on the grant that has funded most of this work. So that's Stephen Bedrick at the Oregon Health and Science University, whose background is medical informatics, and then also Gerasimos Fergadiotis, who's at Portland State University and whose background is speech language pathology. So we have Stephen, who's more kind of computational background, and then Gerasimos, who has more of the SLP background. And then that's also reflected in our research staff, where we have Michaela, who is also an SLP. Myself, my background is computer science, and then Robert Gale, whose background is computational linguistics. And yeah, I just wanted to point this out, that I think a lot of the progress we've been able to make has been really helped by, I think, the fact that we're coming from these different backgrounds and really coming together, and that, we have sort of joint interest in each other's fields. So my background's computational, but I'm really interested in these application areas and in aphasia research. And then same, like Gerasimos is an SLP, but has this real interest in computational models and all this stuff. So I think that kind of joint interest we all share has led to a lot of cool stuff. So wanted to emphasize that. So I'm going to first start by talking about some of the previous work from our team. So we previously worked on automating assessment of performance and confrontation picture naming tests. So we developed this software called Paralg, which stands for Paraphasia Algorithms. And using Paralg, we can automatically classify transcripts of responses from the Philadelphia naming test based on these 4 classifiers. So one is lexicality, so is the response a real word? Then semantic similarity, is it semantically similar to the target word? Phonological similarity, is it phonologically similar to the target word? Morphological similarity. So by using these 4, we can categorize these the main 6 error categories from the PNT. So you can see that here, and this is kind of how the automated process looks. So we have this decision tree model. You have your target and your response that goes in. There's first the lexical decision. So we decide, is that production a real word? If it is, then we have this semantic similarity decision. Is it semantically similar to the target? And then also phonologically and morphologically. And then if it's not a real word, then we just check the phonological similarity category. And at the end, this gives us one of these 6 categories of mixed, semantic, formal, unrelated, phonologically related neologism, and abstruse neologism. So for instance, with this production of cup for the target glass from the PNT, we go through, it is a real word. It is semantically similar, but it's not phonologically similar. So it ends up as a semantic paraphasia by our system. And so just to go through a little bit about how these work. So the lexical decision that's done with a dictionary lookup. The semantic similarity decision is done with a large language model and classifier. And then the phonological and morphological similarity decisions are with a rules-based system that we've automated. So each of these are automated processes that we can run and then take our responses and categorize them into one of these 6 categories. So we developed and evaluated this model using the Moss Aphasia Psycholinguistic Project Database. And performance was measured, well, we measured it partially by F1, or F measure, which is the harmonic mean of the positive predictive value and the sensitivity. And these values ranged from 0.793 to 0.976 across those 6 PNT categories we were considering. So we had a pretty, high degree of success. We were able to automatically decide which of the 6 error categories each of these paraphasias were using fully automated tools. So this was great. And, confrontation naming tests, they are a standard tool in both clinical and research settings. And they do have some advantages. They have a straightforward scoring system, very reliable and valid, somewhat, fairly efficient, and have very clear metrics associated with them. However, there have been efforts to want to kind of move beyond naming and have more effort going towards discourse assessment and discourse work. So effective communication, like as we all, we all know, effective communication at the discourse level is really what's a priority for people with aphasia and their families. And so increasing the focus on that discourse evaluation is important to kind of better understand and treat communication in a more real world context. So there are, these efforts to have discourse measures being used increasingly in research. And discourse assessments can help tailor interventions to target practical needs and hopefully enhance quality of life. So we wanted to do automated assessment now, not just of naming, but also of discourse. So what do we need to do that? So the issue is assessment of paraphasias in discourse is really quite cumbersome. So in order to automatically analyze paraphasias that are made during discourse, you first need a transcription of the discourse, including not only, the orthographic forms of real words, but also any neologisms need to be transcribed in the International Phonetic Alphabet, so it has to be very fine-grained. Once you have your transcript, you have to identify the paraphasias in there, which some of them might be easy to tell if they're neologisms, but if they're real words, it may be pretty ambiguous. And then once you have these paraphasias, you also need to identify targets for them. So what do we think the person was intending to say here? And then once you have those pairs of paraphasias and targets, then you could classify them, or we would want to classify them according to, say, something like the PNT rules. So that's a lot of steps. And the one that we started with was the task of identifying the targets. So we started kind of in the middle there. And we detailed this project in a paper titled Automating Intended Target Identification for Paraphasias in Discourse using a large language model. And I'm going to go into a little detail about like how that model worked and why we kind of started there. But actually first, I'm going to do a brief introduction, very high level, on large language models. So just get us some general ideas of how they work and are trained and what they can be good at and stuff like that. So at their most simplest, so language models are just statistical models of word sequences. And actually, they're not a new concept. Everybody's now talking about like GPT, but simpler language models have actually been around since the 40s. But these newer large language models, like the now famous GPT of ChatGPT, are possible because of a few specific advancements. So one of those is a hardware change. So there was the development of graphics processing units, or GPUs. So those were developed for video games to have better graphics. And those came out, I think the first thing called a GPU was like 1999. But it turns out that that same technology that was driven by the video game industry was actually also great for allowing us to train these deep neural network models on a lot of data. And just to get another definition of deep neural network model, don't need to know a ton about how it works, but it's a machine learning model architecture consisting of a series of layers that transform your data. And another recent change that has led to this is just having so much data now. So with the advent of the internet, we now have these really large digital corpora of language data. So things like all of English Wikipedia or news data or social media data. So there's now just available so much more and just these really large corpora of data to use. And then the third thing I want to mention is a change in theory. And so this is the most recent one where recently there came out this model that is called the Transformer Deep Neural Network Model, and that came out in 2017. And again, you don't need to know a lot about the details of how that model works, but I'll just point out all of the models that we are using are based on that model. And so I'm going to talk a lot about BERT-like models, and so that's based on that. And I'll also point out that GPT, which stands for Generative Pre-trained Transformers, is also one of those models. So these kind of three things together led to this big explosion in all of this large language model research. All right, so large language models are very large, general purpose, deep neural network models of language that are trained on large amounts of data. Until very, very recently, they were typically designed with a kind of two-part training process. So there would be this stage of pre-training where this model is given just tons of text that it learns from and is supposed to learn kind of general purpose representations of language. And then afterwards, you can do a fine-tuning step where you do some further training for a specific classification or representation task. So we're going to talk about BERT, which stands for Bidirectional Encoder Representations from Transformers. So it's another of those transformer models. And BERT was released by a group at Google in 2018, and a version is freely available and can be downloaded locally and fine-tuned. And I'm going to give a little bit of detail, or just very, very high level still, but of how kind of BERT was trained, because we are going to be using very similar conceptual training for our tasks to work with discourse. So BERT was pre-trained through this task called masked language modeling. And you can kind of think of that as like a sentence close task. So, you have a sentence and there's a word missing from it, and a participant is asked to fill in the most likely word, maybe from a set of options. So to do this, the model is given just tons and tons of data, like all of English Wikipedia, with about 15% of the tokens removed or masked out. And then the model learns to fill back in those masked words, and it learns from its incorrect prediction. So if we look here, we have this sample sentence, my blank ate my homework. We would want this model to come out with the prediction of dog should be there. But say it gets it wrong and it guesses cat, then the model is going to have that as one of its errors, and it passes that back through the model, and it shifts its internal structure to decrease the likelihood of that incorrect prediction the next time. So by doing this on enough data, the idea is this model has these kind of general representations of language based upon these words that are co-occurring. And this, now we have this pre-trained model, and again, that can be fine-tuned for a specific task. So yeah, we can download BERT or a related model and fine-tune it. So that means further training of the model. And so here are some examples of the kinds of things you could do with it. So one example would be you can fine-tune BERT to detect the semantic similarity between two words. And that's actually exactly what we did when we developed the newest version of the semantic similarity classifier in our parallel system, is that we trained BERT to do that. You can also use it to do something like classify whether movie reviews are positive or negative. If someone has that on their website and they want them like automatically classified. Or you could use it for something like identifying potential hate speech on social media. So these are these, general purpose models that can be really adapted and fine-tuned for these specific tasks, and a diverse range of different tasks. So how could we use something like this for target identification? So what we noticed was that the task of predicting a target word for a paraphasia that occurs in discourse could be represented in a similar way to mass language modeling. So for instance, if we look at this, collection of sentences from a Cinderella story retelling we have, and then, and she put her foot in and she rode off with the pince, Cinderella was pretty girl. So here we have this paraphasia, pince, and what we can do is we can adjust that sentence and replace the paraphasia with a mask token, and then have the model try to output in a similar way to mass language modeling, or with that same task, what that target word is, which in this case is prince. So that's what we ended up doing, was we fine-tuned a BERT-like model to identify targets for paraphasias that we've masked out. So our data consisted of 332 Cinderella story retellings, and these were from the English Aphasia Bank database. And we did supplement some of that data with data from control participants, but I'm not really going to go into details on that. The Aphasia Bank database, if you're not familiar, has this really large collection of aphasia language samples. So it has these transcribed Cinderella story retellings with audio, and also all these other discourse samples. And it also has test scores like WOB scores and demographic characteristics. So it's a really great resource of a lot of language from people with aphasia. And so paraphasias and their corresponding targets are already identified in the transcripts from Aphasia Bank. We did refine these in some ways, though. So one change is that we kept only the paraphasias that were made to the lemma of content words. And then another bigger change we did was that since we know there's kind of inherent ambiguity in target identification, there could be possible multiple words often in discourse that someone could be intending to say. So we conducted our own target identification task involving having 3 separate annotators look at the transcript and the paraphasias and decide what that target was based on all the information. So the transcript, the audio, the gestures, things like that. And then from those 3, we resolved the 3 targets to one single target for each paraphasia whenever we could. When there was too much disagreement, we had to just remove some. But for many of them, we were able to take these and resolve to one robust target. And so we had a total of 2,489 paraphasias after this filtering. And one thing to note is that out of the targets that we could resolve, which wasn't all of them, but out of those, the average agreement between the human annotators was 76.8%. So that means, I just want to kind of point this out as, this is a pretty difficult task even for humans, for like, it is really hard to say in discourse exactly what we think someone was intending to say when it could possible, multiple words could make sense there, So it's a pretty hard task. But we do now have a robust set of transcripts with paraphasias and their identified targets. The last thing we did was we set up this 10-fold cross-validation. So that means we split the data into a training set and a testing set 10 separate times. And the purpose of doing that is to help us avoid overfitting. So with tuning these models, sometimes it can pick up on like weird idiosyncrasies in your training set or something like that. So we wanted to make sure the models are learning more like general information. And so by looking at how it does on unseen testing data, it's kind of a more realistic test of its performance. So we set up the data, and now we have this data that we can fine-tune our BERT model with to do this target prediction task. So, sorry, okay. So here's how that looked. So we have here a sample. This is just part of the full transcript that goes in, but we have the same set of sentences with the one paraphasia masked out. And it goes into our pre-trained BERT-like large language model. It has this classifier layer at the end. And then the idea is at the end we have the probability that that masked out token is one of each of the words in your vocabulary space. This is, not exactly what's happening, but basically this. And so the idea is that we would want this model to have the highest probability that the missing word here should have been prince, which would mean that the target would be prince. So we do this on all of the data, all of the transcripts, with each of these sequentially masked out. When the model gets things wrong, it shifts its classifier layer as well as the internal structure of the BERT large language model accordingly. So it learns from these mistakes, it shifts the representations to better reflect our task. And by doing this on enough of the training data, the model can learn to do the same on unseen testing data. And so here were our results. So out of the 2,489 paraphasias, we were able to get the exact resolve target as the first prediction from the model with 50.7% accuracy. And then if we give the model 5 chances, so we look at its top 5 predicted targets, then we get up to 69.5%. And, so this accuracy, I mean, it's maybe not as high as we would want. But I want to point out, like, if you were to do this by chance, your accuracy is like 1 out of however big your vocabulary is, hundreds of thousands. And so it is really a quite difficult task. And considering how hard a time humans have with it, looking at 50% accuracy is not as bad as it may seem. And then we also did these stratifications of the results. So we looked at human agreement. So we had those agreement statistics for each target, and we separated into the ones that the humans all agreed on versus the ones they didn't. And our models do better on, or our model does better on the one that humans all agreed on. And then same with confidence. So we had the human annotators rank their confidence in the targets, and the model also does better on the same targets that humans were also more confident on. And so this makes sense because, those are kind of indicative of those are the easier ones to identify. So it makes sense that our model is also finding those easier. And then we also did a couple stratifications by some clinical characteristics. So we have the results stratified by the WOB-AQ scores to capture severity. So we have that the model does better on patients with less severe aphasia by the AQ, and worse when they have more severe aphasia by AQ. And then similar pattern with fluent participants versus non-fluent participants. We are seeing higher accuracy for fluent participants and lower for non-fluent. So overall around 50% accuracy for exactly getting the top target. And then if we give it 5 chances, up to 70%. And one thing I can note also is that I didn't put it here, but if you give the model even more chances, once you get up to 20 chances, you get up to 80% chance. So you can see, like, by, the model is often finding it within its top predictions, even if it's not the very first one. But it seems like there's room for improvement. So one thing we noticed is, when humans identify the target for their, if these paraphasias, they're not just using the surrounding language like we are in this mass language modeling task, but of course they use the paraphasia itself. That can have valuable information about what the target word should be. So by removing the paraphasia, we're getting rid of that valuable information. But the problem is the large language models are not designed for text other than orthographic text. So we have to have transcripts that have, orthographic text, but also these non-real words that are transcribed in IPA. And so this was kind of a missing piece where the large language models were really not set up for that. So our team member Robert had the idea, what if we teach a large language model to meaningfully represent IPA? And so that's what we did. So we have this model called BORT, which stands for Beyond Orthographically Restricted Transformers. So this model was built on an established large language model called BART, which again, you don't need to know a lot of details of, but so BART kind of combines some architecture from both BERT and GPT. And so the way that we trained BORT was that we did this additional pre-training task on top of the BART model to allow the model to represent IPA. And the idea was we wanted BORT to be a general purpose large language model for speech language pathology tasks that require these transcripts with a mixture of orthographic and phonemic transcriptions. So there are full details on BORT in this paper, but I'm going to give an overview of it here as well. Okay, so BORT was given some combination of 3 different pre-training tasks. So one task was given a sentence with a word in IPA, convert that to the same sentence with the word replaced in its orthographic form. So we have this sentence, he retaliates by spreading false rumors. We want to take this transcription in IPA and convert it back to orthographic. Same with a task for spelling. So we have given a sentence with the word spelled out. We have the model convert that to the same sentence with the word in orthographic form. So we have here retaliates, spelled out, and then we want it back to the orthographic form there. And then finally, on either the pronunciation task or the spelling task, we sometimes have some noise. So that means some amount of tokens inserted, deleted, replaced, and then the same task. So here, instead of retaliates, we have this kind of one with some substitutions, and then we want it to correct back to the original word before the noise is added, and in its orthographic form. All right, and so we used English Wikipedia for the pre-training data, and we used the CMU dictionary for getting the pronunciations in IPA. And so we tried different combinations of the three tasks of pronunciation, spelling, and noise. And so this kind of summarizes that whole process I went through, but I'll go through this bit by bit. So we have our initial weights come from the BART large language model already released. Our data comes from Wikipedia with the pronunciations being pulled from the CMU dictionary. We do these transformations, so either pronouncing words or spelling words or adding some noise to either of those. And then we have some combination of those. So either with pronunciation alone, spelling alone, or both, with or without noise. And we give it this transformed text and have it try to get back to the original text. And we found that this last model, the one that used all three, so the pronunciation task, the spelling task, and with noise, was the best one. So that's the one that we use moving forward. All right, so now we have this model, which is a pre-trained large language model that can accept transcripts with a mixture of orthographic and phonemic transcriptions. And importantly, these phonemic transcriptions are meaningful. So by doing this task where we've had it map between IPA and real words, it is able to attach some representation to those characters that carries meaning. And so now we can fine-tune this large language model to predict targets for paraphasias in discourse, and we no longer have to remove the paraphasias when we do it, so we can leave them in and do the same task. All right, so we used the data again from English Aphasia Bank, although this time we actually included not only Cinderella story retellings, but also the other discourse tasks in Aphasia Bank, which included like the PB&J, how to do a PB&J, and a few others. And we used the paraphasias and the corresponding targets that were identified by the Aphasia Bank annotators. So I need to point that out that the data that we're using for this version is a little different from what we had before. So we have this more broad set of data, and also the data quality is not as high. So we don't have the robust targets that we had before. So keep that in mind for when we will see the results. So we set up the data so that instead of doing masked language modeling, the paraphasia is left in and identified by angle brackets. So this is just one sentence. We would put in the whole transcript, but we have, she made a pumpkin, the beautiful ha-drawn castle. And here we've noted that the paraphasia we want the model to be looking at is this one encircled in angle brackets. And we want the output to be the target for that, which in this case is pumpkin. And again, we use tenfold cross-validation. So then this is what the tuning looks like. So we feed in, again, our whole transcript. I have the one sentence here, but whole transcript, we have the specific paraphasia we're looking at encircled in angle brackets. That goes in to our pre-trained now BORT LLM, and then we have a classifier layer. And again, at the end, we want, so our hope is that the prediction or the probability that the target is pumpkin is really high and the others are low. So then we end up choosing pumpkin as the target. But again, as the model gets things wrong, it passes that back through the error back through the model. So it shifts the classifier layer and the internal structure of the large language model accordingly. So by doing this on the entire train split of the data, the BORT should learn to identify the targets given both the surrounding language of the paraphasia and the paraphasia itself. And so here are some results. So we tested on the test data that hasn't been seen before, and we evaluate the results using both the accuracy of the exact match and giving the model 5 chances, same as in the previous results. But unfortunately, we don't see a really big improvement. So we get up to 0.533 accuracy of exact match and 0.712 given the 5 chances. And so, this isn't, as much of an improvement as we would hope, but do have to remember that this was that different data. So this is just filtered to the Cinderella, by the way, even though the training had all of them. But looking at the Cinderella results, we include in here all the targets, including ones that it turned out the humans could not agree on what that target was. So really, this is a bit of an underestimate of the performance. But yeah. So there's some room for improvement, but there's a lot of promise that this kind of method can be useful. And importantly, we can also use BORT for other tasks. So now we have this, pre-trained large language model that can accept these transcripts with orthographic and phonemic forms, and we can use that for other things as well. So back to what we're doing here of trying to analyze paraphasias made during discourse. We've done some work on the targets. What about identifying the paraphasias? So that's what some of our most recent work is on. And these are actually preliminary, unpublished results, so things may change. But this will be at a poster at CAC next month. So more details there. And then we're also going to write a full publication of this. Okay, so how can we instead fine-tune BORT to identify the paraphasias? So the way that we set this up was as a binary classification task. So for each word in your transcript, the model decides whether that word is a paraphasia. Like yes, no, is it a paraphasia? Is it not? Again, we use Cinderella story retellings from the Aphasia Bank data. For each word in the transcript, we put angle brackets around that word and then had the model identify whether that was a paraphasia. And so here we can see some sample input. So given this, set of sentences, we have right here, we're looking at pretty. We've put angle brackets around that, and we want the output to be that that is not a paraphasia. And then here we have the word curl, and we want the output there to be that that is a paraphasia, where they were probably intending to say girl here. Cinderella was pretty girl. So this is how that would be structured. So one issue is preparing the data like this, where we have this, it turns out that we have 93,842 total tokens across all of the transcripts, and only 3,107 of those are actually paraphasias. So that means that when doing this like a classification task, we have a very imbalanced data set. So you can note then, if we had a classifier just say, oh, nothing here is a paraphasia, these are all non-paraphasias, that classifier would be getting 96.7% accuracy. So it would look like it's doing really well. But if you look at the specificity and sensitivity, it would have perfect specificity because it get all of the non-paraphasias, but it have 0 sensitivity where it hasn't caught any of those paraphasias. So due to this issue, we did a couple different things. So one is when we were fine-tuning, we did some adjustments to training to account for this, where we did some weighting of the class sizes. And then we also make sure to look not just at accuracy when we look at performance, but we really look at sensitivity to properly evaluate this. And again, to prevent overfitting, we use tenfold cross-validation. So yeah, so this is what this looked like. So we feed in, this should look kind of familiar. We feed in our transcripts with the angle brackets, and it goes into our pre-trained large language model and then a classifier layer. And here at the end, instead what we have is we want it to predict whether or not that word is a paraphasia. And so for pretty, we want this to have low probability of being a paraphasia, and for curl, we want it to have a high probability. And so, yeah, so we fine-tuned BORT to do this on all of the transcripts for each word and each transcript in the training split. And again, as the model gets things wrong, it shifts both the classifier layer and the pre-trained BORT model to reflect that. And our training involved balancing for the different class sizes. And by doing this on the entire train split, the idea is that that BORT will learn to identify both non-real word paraphasias, so ones that are in IPA that may be easy to see, but then also the harder ones like curl here, that is a paraphasia, but it's a real word. So you have to, think a little harder to get there. All right, so here are some of our results. So we have sensitivity of 0.625, so quite a bit lower than our specificity, which was at 0.987, and our positive predictive value at 0.685. And then, really high accuracy, but don't really want to look at that too much. And so one thing we noted, so the sensitivity is not as good as we would want. So sensitivity is probably what we care about the most here, because we want to really be capturing these potential paraphasias. And one thing we notice is, the built-in threshold for making this classifier decision is 0.5. So if these predictions are below 0.5, you would say not a paraphasia in the top row. And if it's above, then it would be a paraphasia. And so we thought about, well, what if maybe we want to shift that cutoff, that threshold. And so what we did was we did some ROC analysis. So we took in our prediction probabilities and did this technique, which allows us to find what threshold balances the sensitivity and the specificity. And we thought this would be important because we care more about sensitivity. Even if accuracy goes down some, what's most important is having that higher sensitivity. And this really did improve our results by that metric. So we turned the threshold actually way down. The optimal one was all the way at 0.044. And this raises our sensitivity all the way up to 0.867. And specificity lowers a little bit, but still pretty good. And the biggest one that's quite low now is positive predictive value. So this is because now we have a lot of false positives. So yeah, so basically what this means is, like, out of all the ones that we say are paraphasia, only 27.8% of them actually are paraphasia. So it's a good bit of false positives, but we felt that this was better for the use case where we imagine a scenario where you have some automated system that can identify these paraphasias, but then a clinician would be using this tool and kind of narrowing down from there. So it'd be better to have more of them captured at first and then narrowed down. And so this kind of highlights that. So we have this paragraph from, so this is a Cinderella story retelling, and this has a heat map on it. So on each word, we have highlighting, where the amount of highlighting on the word is proportional to the prediction probability. And so darker highlighting represents a higher prediction probability from our model. So this is what the trained model predicted for this unseen retelling. So we can see that it says some are more likely to be paraphasias and some, oh, maybe, but like not as sure about. But with our lower threshold of 0.044, actually all these ones where the highlight is really visible were classified as potential paraphasias by our model. And it turns out actually there's only two paraphasias here, this one and this one. But so we have caught both of those, but then we also have all these other false positives. But the idea is, you could look at this and have really quickly see what some possible ones are. You'd be like, oh, okay, yeah, that's a paraphasia. No, why does the model think mopping is a paraphasia? That makes sense here. And oh, which, yeah, that's a paraphasia. So it kind of could like speed up that process a bit. All right, so where does that leave us? So we have good attempts at the identifying paraphasias, identifying the targets. What about the transcription? So that's really important. Transcription is very labor intensive. How can we use something like automatic speech recognition for that? And so there is some potential there, but the ASR systems that are used currently, like if you're familiar with Whisper, they're really quite high quality, but they're not designed for phonemic level transcriptions or aphasic speech. So they're really designed to give you orthographic transcriptions and to not expect many errors and or not as many as you would have in aphasic speech. And so we do have some promising work on developing ASR for aphasic speech. So this was in our post-stroke speech transcription challenge. And so there's more details in this paper. But that work had been for naming, and most of the work we've done around this has been for naming. So we do hope to eventually expand it to discourse, but that'll have to be a next step. And then what about the last step of the classification? So this one we should be able to do. We can adapt the paralg, which we had working for PNT target paraphasia pairs. We should be able to get that also for these more general paraphasia target pairs as well. So yeah, so some takeaways, still more to do, but we've made some really good progress, especially on identifying paraphasias and targets in discourse. And some more takeaways. So yeah, advancements in computing have allowed these large language models to be developed, and they're really exciting and can do a lot, and we can harness them for this automated discourse analysis. But it's really not simple, and very careful, deliberate work must be done to adapt these models for working with discourse from people with aphasia. And I also think that, emphasizing again, I think interdisciplinary work has been really great here, where we really have both this computational input and SLP input all throughout the process of developing these models. And there's a lot left to do, but we do have high hopes that these models can eventually become useful clinical tools. So I have some references here, and then we have funding or this work is supported by funding from the NIH. And thank you for listening. I'm happy to take any questions, and we also have Gerasimus available for questions as well.
Thanks so much, Alex. You presented some pretty sophisticated work there, and yet for all of us who are not computer scientists, you've presented it in a pretty clear way, which is not always the case. So I just want to credit your team, first of all, that you have been working with AI and language models long before GPT. So you're very much not on the bandwagon, but you have been at it for a long time. So I think it's important to point out.
Mhm.
And I think what strikes me about this work is that it is very well grounded. Like you're in no way is the team just throwing AI at this problem, but each step is, as you said, carefully and deliberately chosen and really theoretically motivated. So yeah, incredible work.
Thanks.
A couple of questions I have, and if people want to enter any in the Q&A box. One is, 3 days ago, Llama 3 has been released by Meta, which is apparently the latest and greatest. And then in the last 24 hours, Phi 3. These language models just keep coming and coming, and they're all competing. To what extent do you think improvements in the language models themselves could push up the results of this kind of work? Or do you think it's actually there's a ceiling there and it's more about the other aspects of the technology?
Yeah, that's a really good question. It's interesting. So, with the really, really large language models like those, like Llama, one problem is they are harder to fine tune. Like people don't really fine tune those models. You use them in a like out of the box way, and you do some
Mm.
prompting with them, but you aren't actually tuning it for your specific test because they're supposed to be good enough that you don't need to. But I think for these like really specific constrained tasks, often you actually do want something that you can more easily fine tune. So I think there's that. And then I don't really remember with Llama. I think it's pretty close to GPT in terms of architecture, but there are some things where like I'm not sure that architecture would be quite as good for this task, which is a classification task, where
Mm,
that might be better for more generative tasks that need things like question answering or summarization or things like that. Well, we use these more BERT-like models that are more designed for or they're really good at classification. So there are a couple things there, but I mean, it would be cool to see though, like how some larger models do. Oh, the other thing is that those large like I don't know what Llama's representations of IPA are, but I would assume it's pretty minimal and that they haven't seen very much IPA and wouldn't have much meaningful representations there. So that would also continue to be a problem with the models that are available.
mm. Gerasimus, thanks for joining us for the questions, and do jump in if you'd like. Question in the chat from Ben Carter is maybe a similar vein, is would more high quality training data mean better results? Seems that's a real challenge, so the IPA transcription could be key.
Yeah. Yeah, I mean more aphasia data would be great, and yeah, more high quality would be great. We do have plans to do more of that robust target identification to get really good labels for other discourse tasks besides the Cinderella story. So all the other ones in Aphasia Bank, we're hoping to do a similar task. So I think that would be um, really great. And yeah, I don't know if that answers the question, but.
Mm. I mean, with BORT, is there a tolerance for multiple acceptable pronunciations, or even people transcribing things slightly differently? I'm assuming it's not a one-to-one relationship. It's kind of got a similarity between different transcriptions and an orthographic word. Yeah.
Yeah, so if you were going to, yeah, I think that especially with that noise it had, when it did its pre-training, where sometimes it would get perfect pronunciation, but then sometimes it would get noise on the pronunciation. That gives it some of that like flexibility where,
Mm.
yeah, it would probably be able to map one that's like slightly off back to one that doesn't have that noise in it. So. Yeah, the representations should be able to handle that kind of like slight variation.
Yeah. So I guess that's the difference between training it and just feeding it a dictionary.
Mm-hmm.
Anonymous question, what do you see as the main use case for this technology? Primarily assessment, or are there therapeutic or compensatory uses you envision? I guess, what's the long-term vision?
That might be a better question for
Yeah,
Gerasimus.
I'm happy to take that one. So initially, the primary motivation behind this line of research was to use these tools to automate assessment applications. So we started in the context of confrontation picture naming tests because they don't have the ambiguity of what the target is. So the work that Alex showed early in the presentation, where we have this set of algorithms that classify errors. And the idea would be to embed those in a pipeline where during confrontation picture naming tests, in addition to having like an ASR system, we will have a machine that will dynamically online do the error coding, so that you could be error coding and creating profiles of strengths and weaknesses of people with aphasia. And similarly, because when we do the confrontation naming test, we get a lot of information for individuals with aphasia, but that doesn't tell us like 100% like what the person's profile will look like in connected speech. So we want to be able to sort of like create these profiles again for connected speech in an assessment framework. Having said that, it's easy perhaps for someone to see, with some caveats, how some of this technology could be used potentially in AAC devices or as compensatory strategies if a person with aphasia has a way to, in the moment, like generate a list of potential things. If they produce a paraphasia and have some sort of like system in front of them that recognizes or gives options for potential like targets. Now, having said that, I'm one of our teams like well, we recognize that there is a risk there. We don't want machines to be actually being asked to tell or predict what a person was trying to say, right? So there are some issues that need to be resolved, but it's potentially something that we could explore in the future as well. But like for us, primarily it's assessment, the primary motivation at this point.
And I suppose that the highest target is discourse because it's the richest, it's the most meaningful, but also the most challenging data to analyze, for clinicians and then for AI as well, starting at speech recognition.
Yeah, absolutely. Yeah.
Question from Archie Adakari. Thank you for this great presentation. Are you focusing on extending this work to accommodate errors in free-form conversations by people with aphasia?
Like outside of Cinderella story or?
So I think what you just touched on, Erasmus, is compensating for errors within a conversation, that conversational augmentation perhaps is what it means.
I have some thoughts. Well, Alex, like if you want to take a minute, think about it. But one of the things that, if I understand the question, like one of the things that made us start with a Cinderella story, which is still connected speech, people still have the flexibility of producing all sorts of different, morphosyntactic constructions and also have like vocabulary, is that it's not completely unconstrained. There's still some sort of like topic. So the vocabulary is a little bit like there's some constraints there, right? There's a topic, whereas in like free form like conversations, depending on like if you don't know the topic, we thought that training a machine to be able to handle like all sorts of interactions, that would have been much more challenging. We found it like potentially helpful to have the topic a little bit constrained. Now, we don't want to make it so that our approaches work only with the Cinderella story, but oftentimes in aphasia batteries, there is this picture description or some story description, right, that people have to produce. So we want to make it so that we wanted to make it so that initially our system would work with those more constrained type of discourse types. We haven't tried it with like free speech, I think, because we think it might be a more challenging task at this time. So I don't know if you, Alex, want to add anything else?
Yeah, I mean, I think in the Bort paper we did that one, it was trained on all the aphasia bank discourse tasks. I'm not sure if any of those would quite be what you're describing in terms of free form, but some of them were less constrained. So, and I think that performance was low. I'd have to look. There is performance stratified by those different or look at the different discourse types, and I do think that the ones that were more constrained we had higher performance on, which would make sense. But like I know that's true for Cinderella, was a little better than some of the others. But yeah, no, I think that, yeah, the less constraint you have, the harder it gets, because you could be trying to say anything. So yeah.
Just like with humans, I guess.
Yeah.
Did you include the from the aphasia bank, the tell me about your stroke, or tell me about a happy memory, I think that's fairly open.
Yeah, those are could be pretty open.
Yeah, I mean there's gonna be themes obviously, but
yeah.
Okay, and what is the additional data that you think might push the accuracy up higher? I mean, I can imagine biographical knowledge and for either paraphasias or target identification.
Yeah, I don't know. I'm trying to think of what, I mean, I just think just more of it, and more diverse data. We've talked about that needing like, different people from different regions with different accents and things like that. And as much more data as we can get really is important. Again, there's that robustness of wanting data that has really as clear labels as we can get, so that there's less noise in our model. I don't know, other than Drosmos, do you have any other ideas?
Well, I think one of the things and that might be more of a cue for you to talk about is like multimodal mobiles potentially might be one thing that we're discussing, where we might have the opportunity to allow a machine to use not only what was said, but also what was the pictorial content, what was like in the pictures or in the story, when the person was actually generating their discourse. So that might be able to potentially give a boost to the performance of the machine if it knows what was the picture that the person was like looking at, when generating the description, that might be something. But like Alex said, one of those limitations here for us is that access to data. Like we working in aphasiology think that like a sample size of 40 people with aphasia is huge, right? And aphasia bank having 300 cases is like, oh my God, that's but if you actually look at the kinds of applications that the people who work on machine learning, what kind of data sets they're looking at, we're talking about a lot of data points, right? So that is sort of like one of the biggest sort of like limitations that we have right now is how do we train those machines and access to the data sets.
Yep, I think Aphasia Bank's getting quite the workout in the last 2 years.
Yeah.
I see a paper recently came out where they used YouTube recordings of people with aphasia, just scoured YouTube and used those for training something, which is interesting. Yeah. All right. Look, last question is what's the very next project you're working on? I'm sure there's a few, but anything you can tell us about?
Well, there's more expansions of this paraphasia identification work. So more looking deeper into what's going on with that. But some other stuff like Drosmos was mentioning, the multimodal. So part of we hadn't looked at like, yeah, when someone names something that's a part of the picture of the PNT instead of like the whole item. So being able to tune to that and yeah, identify those would be helpful. And then yeah, we could use some models that incorporate images as well. And then there's also what is some other, oh yeah, multi-word productions with another one, actually Paralg. Again, these are more in the naming, but Paralg is designed for one-word responses more than multi-word. So wanting to expand out of that for our error classification as
So
well.
like a short phrase, like the pretty girl,
yeah.
or right?
Yeah.
Yep.
Exactly.
Well,
And
look, I could keep talking about. Oh, sorry. Go ahead, Jairus.
I know, just very, very quickly. And I think the main, like the end goal here is to be able to create at some point something that starts with ASR and ends with like having identified errors and having classified them. So initially, like our first steps were to sort of like start creating some of the parts that are needed for this, and we're moving towards sort of like integrating as much of those as possible. So we have like this pipeline that is both like helpful for clinicians, but it's also realistic to implement.
But ASR is such a, I mean, it's now fairly accurate with non-aphasic speakers, but the pauses, revisions, paraphasias. I mean, how do you train a model to do that? So, yeah, but bit by bit.
Yep.
So thanks both of you again. I could keep talking about this topic for quite a while personally, but we better draw it to a close. So I'm just going to tell people what we are doing next month. If you would like to re-listen or recommend today's seminar, you'll find the recording on the Aphasia CRE YouTube channel pretty soon, along with most of our previous seminars. And you can always stay up to date with us through various social media channels. And that's where you will hear about next month's seminar in more detail, which is Dr. Lisa Anima from the University of Queensland presenting the results of a very large co-design project, Understanding Unmet Aphasia Service Needs and Priorities Using Experience-Based Co-Design, a Blueprint for Aphasia Service Development. And that'll be at 3 p.m. Melbourne next month. Thanks to both of you. And we'll see everyone next month.